This is a recent upload from Dave Weiss, so let's listen to Dave's logic.
Okay, the question is asked, how can a 3-foot wave block a giant ship from a 6-foot tall man? So here I have a bunch of pencils on the floor. They're going all the way across the room. You'll see them a little better as they go down. And you see the space between them is equal. But as they go down, the spaces get compressed. As we go all the way down, we see basically from here to the bottom of the screen is about the same as all of the other 30 spaces, however many there are.
So yes, the pencils are evenly spaced, and the pencils above are compressed into the same space as the space below. Now this phenomena can be explained with this orthographic view, so here we have two 10-foot segments, and it's pretty easy to understand why the observer sees the farther segment as a smaller angle than the nearby segment. So again, not only is the next angle smaller than the previous angle, we see the angles converging up to eye level. And this pattern continues as the segments get farther away. So this is why we see the pencils appearing closer and converging up to eye level. And this is also why the horizon appears to rise to eye level, since the same pattern continues as the ground gets farther away from the observer. Now here's another thing to notice. Even though all of these pencils have compressed into this small area, the angular size of the bookcase really has not changed at all.
Right, they're all getting compressed. Now, if I got another pencil and put it on top of, let's say, the 5th pencil from the end, it would block all of the other pencils.
I agree that the yellow pencil on top would block all the rest of the pencils. But how much of the bookcase did it block? And Dave, did you consider that the yellow pencil on top also gets smaller with distance?
Now, we live on a flat earth. A 6-foot tall man looking down at the water is looking down 6 feet. If he looks down at the water here, he's looking down 6 feet. Out here, it's still 6 feet below his eyes. But the angle changes. So let's watch what happens. We move that wave out and look at the gap between where he can see the water and where the wave is. It gets longer and longer. Look how wide it is now. And it's really wide.
So yes, the amount of water beyond the wave hidden by the first wave is shorter than the amount of water hidden by the second wave. But are we talking about a single wave obstructing the bottom of a ship or the surface of water beyond the wave?
This was an orthographic view. Nobody sees sideways, but this is what's going on. But this is how we really see. And again, here's an orthographic view again.
Well, good, Dave. I'm glad you understand that the orthographic view does show how perspective works, because that was something I was able to prove with this video that I uploaded about 1.5 years ago. I started with this simple question: why do these parallel lines appear to converge? So will it be the flat earth perspective orthographic view, or the scale orthographic view below, where we see the angular size changes for each pole as they get farther away? So let's see what caused this. So I'm backing away, turning 90 degrees to that railing, and surprise, surprise, it looks exactly like the orthographic drawing. Now this is really a no-brainer, because perspective is based on the actual sizes and distances of objects from the observer, and that's exactly what the scale orthographic view represents. The drawing above shows the position of the camera when I made that video and why that second pole appears smaller in angular size. And each pole appears smaller and smaller as they get farther away from the camera. And if that railing was long enough, those angles would eventually converge to the vanishing point, which is an angle that is too small to resolve.
Again, here's an orthographic view again. So we got our boat right here, we got our guy right here, we got our wave. He's blocking the bottom of the boat, but he could kind of look over the wave a little bit. And if we put the ship out here, he can still see the whole ship down to the water line. Farther out, he can still see it, he can still see it, he can still see it. Makes perfect sense. So now I move the wave way out here. Now, even though it's smaller, it's still 3 feet above the flat water. And let's take a look. So here's our perspective grid. It gets this amount of information. Let's say this is 1 mile, right? 1 mile, that's a mile, that's a mile, that's a mile. Those miles are getting compressed more and more and more. If I zoom in, each one of these is a mile, and it's getting compressed until they're literally on top of each other.
Now here's some screenshots from that last clip. And Dave used the orthographic view to explain how the observer sees perspective. But then he jumps to this graphic claiming that the wave is 9 miles away. So what happened to these angles converging up to eye level? Would a 6-foot person really be looking down to the water at 9 miles? Is there a way that we could estimate at what distance the horizon would be for this 6-foot person on a flat Earth? Now, Dave has already said that he agrees that the orthographic view explains how visual perspective works. So we should know that we can calculate the size of this visual angle by using this trigonometric formula. Now, since this is a scale drawing, we can see that the measurement on a protractor for a 6-foot height at 30 feet matches the calculation for that same height and distance. This is also true for a 6-foot height at 60 feet. Now, when I do a calculation for 6 feet at 1 mile, I get 0.065 degrees, which is less than 1/10 of a degree. Now, if we compare this to a person with 20/20 vision, that's a visual acuity of 1 arc minute or 0.017 degrees. So what does 20/20 vision mean and how is it measured? Now, I'm sure that everybody is familiar with the Snellen and eye chart. And if you're able to read this row, that means that you have 20/20 vision. So the Snellen system assumes that a normal eye has good acuity if it can resolve certain details in a letter at 20 feet. Those details are described as the distance at which each element of a letter, for example, a letter E, has the angular height of 1 minute of arc. 1 minute of arc is equal to 1/60th of a degree. The entire letter makes up 5 minutes of arc. So each letter is 5 arc minutes in height and width, which is 0.083 degrees. So again, at 1 mile, the angular distance of the water below this 6-foot eye level is 0.065 degrees, which is less than the angular height of 20/20 letters on an eye chart. At 3 miles, this angle is reduced to 0.022 degrees, which is a bit bigger than each segment of that letter at 0.017 degrees. So this is close to the limits of resolution for a person with 20/20 vision. Now at 4 miles, the calculated angle is 0.016 degrees. So I think we could agree that at this point, this would be the vanishing point. The water beyond 4 miles is non-resolvable. This means that the estimated distance of the horizon for a 6-foot person on a flat Earth at the seashore is about 4 miles, and this is only 1 mile longer than the geometric horizon for the globe. Now, if we add 3-foot waves, that angle is reduced to 0.008 degrees, so it's pretty obvious that waves beyond 4 miles would also be non-resolvable. Which definitely means that you're not going to be seeing waves at 9 miles unless you have a P900. I'm sorry, Dave, but that graphic does not represent reality for a flat Earth.
Area, it's just going to get smaller and smaller. This is his line of sight. He can't see the water until over here.
What the? Did Dave just say you would see water past a wave at 9 miles?
This is his line of sight. He can't see the water until over here.
Yes, he did.
Because all of that distance is compressed into this small space, the boat's just going to get smaller and smaller and smaller, and it's not really going to move farther in your visual space. It's just going to disappear. The entire boat can disappear behind this small wave.
So according to Dave, this is how a 3-foot wave can block a tall ship from a 6-foot man on a flat Earth. So here's a wave at 9 miles and you can see water beyond it, just like Dave said. Here is a cruise ship beyond that wave. So the ship appears smaller as it gets farther away, and smaller, until the ship disappears behind the wave. Dave, are you serious? I think it's time for a reality check. I'm sure many of you are familiar with this video, and I'll leave a link in the description. Here's a screenshot from that video with some information. The camera height's about 33 feet. To the right is the Epic at 4.8 miles. The calculated distance to the horizon is 7 to 7.6 miles. And in the distance at 16 miles is the Conti Lion. So Dave, do you really think that these waves we see on the horizon are hiding the hull of this ship? Common sense says no. And Dave, do you really think that the non-resolvable waves on the horizon in this photograph are hiding the bottom half of the sun? Again, common sense says no. So sorry, Dave, but observed evidence does not support your hypothesis.